Okay, so let's start for today's lecture. So welcome back. So recall that last time we have proved this very important Huysken's monotonicity formula. So let me remind you what that is. So let's say you have a mean curvature flow denoted by calibrated n, and the time slices are sigma t. So these sigma are in Rn+1. So mostly in this lecture, throughout these lectures, we only consider hypersurface case, the codimension 1 case, okay? N-dimensional mean curvature flow in n+1 space. And pick a point that you want to consider, say x0 is in the time t0 slice. So without loss of generality, by translation, you can always translate the point that you want to consider to space-time 0. By translation. And then the Huysken's monotonicity formula tells you that d dt of this integration of the backward heat kernel on the evolving hypersurface is equal to negative, again, rho. So the backward heat kernel centered at the space-time point x0, t0, and the mean curvature of the evolving hypersurface, and then minus the position vector projected to the normal direction divided by 2t squared. And you are integrating with respect to the induced measure on the hypersurface, where, let me remind you, the backward heat kernel centered at x0, t0, that is just the Gaussian integration, right? This coincides with the Gaussian distribution in probability theory, and it satisfies the fundamentals. It is the fundamental solution of the heat equation, right? And this is an n-dimensional backward heat kernel. It's not the n-dimensional, n+1 dimensional. Right. And what did we obtain from this monotonicity formula? We were able to do blow-ups, zooming in a singular point, possibly. So the x0, t0 that you are considering are possibly singular space-time point of the mean curvature flow. So we do parabolic rescaling. So this was introduced in the first lecture by a sequence of factors. So the rescaling factors, let's choose, because we want to zoom in, so we want to choose a sequence of rescaling factors going to infinity. And the parabolic dilation, and this is equal to, so we defined this in the first lecture. You scale, the scaling in time is the square of the scaling in space. This is parabolic rescaling. This is t over lambda I square. So you scale the time t over lambda I square slice by lambda I. So this is your sequence of new flow, and we denote it by sigma I t. filter. So for each I, you get the new flow. And parabolic rescaling of a flow is also a mean curvature flow. And last time we have proved that for any, so this is a backward rescaling. So for any A less than B less than 0, so these are time slices, we have proved that the integration from time A to time B of this sequence of rescaled flow. This is what we have obtained last time. Pi t. So this is the backward heat kernel. Let me write it down. X squared over 4t. H minus x perp over 2t squared d mu integrating on the hypersurface. This is going to 0 as I going to infinity. Right? So what have we obtained? So this tells you, because this is for any A and B. So we have this sequence of new flows converge to a limit flow. So I haven't made this legitimate that you are able to obtain a limit flow. This is, you need some compactness theorem that we will get to perhaps the next time. So you will be able to extract after possibly up to a subsequence. These are because you need the compactness theorem, so passing to a subsequence. It's not legitimate yet. To a limit flow on any compact subset of the backward spacetime. Negative infinity to 0. So let me move this. Okay. And moreover, because this backward heat kernel is always positive, so in the limit flow, this is equal to 0, and which means that the limit flow, so moreover, sigma infinity sub t satisfies h infinity sub t and the position vector at infinity sub t projected to the normal direction is constantly equal to 0. Okay. So these are space-time convergence. So we from this we can also get the time slices convergence. Right. So this is converging for any time interval A to B. And by Fubini's theorem, in the real analysis, if it converge in the time interval, the integral, then it should converge for almost every time slice. Right? Which means that you can choose a C in AB such that lambda I, this rescaling sequence at this fixed time, converge to the time C slice of the limit flow. And recall that we have the property that the limit flows satisfying this equation are evolving by self-similar shrinking. So self-shrinking. we have deduced last time that if a flow satisfies this equation, then it evolves under mean curvature flow by this self-similar shrinking. So the time t slice is equal to scaling by time negative t of the time -1 slice. Okay, so this is the -1 slice. So these are self-shrinking solutions, which means that this is equal to time -1 slice rescaled by square root of -c. Okay. You put this back, you divide both sides. So we want to get a converging subsequence at the time -1 slice, okay, which so this is the time -1 slice of the limit flow. Okay, the limit flow. So which means that up to a subsequence, so if you choose, if choosing Ti equal to C over lambda I square, then we have this rescaling factor is actually 1 over square root of -Ti, right? Of Ti is converging to the time -1 slice. And as a time -1 slice of a self-shrinking solution, you plug in time -1 here. So in the previous page, if you put in t equal to -1, satisfies an elliptic equation plus x perp. So this is called the self-shrinker equation. And so we call the flow, the limit flow is self-shrinking flow. And we call the time -1 slice to be the self-shrinker. So this is just a conventional notation. So seems that previously at a certain time, they called the time -1/2 slice the self-shrinker, but doesn't matter. So we just call the time -1 slice to be a self-shrinker. And all other time slices are just rescalings of this particular time slice. Okay. Any questions? Okay. Sorry, let me add a few more pages. Right. And recall that last time we also have introduced the notion of type 1 and type 2 singularities. So we call type 1 if we have supremum of the second fundamental form square at the time t slice, and u is less than a uniform constant divided by t, where c is less than infinity. So means that as time go to 0, as time t go to 0, from backward, the curvature is not blowing up too fast. It blows up at most at the rate of order 1 over square root of t when you take square root on both sides. And we call it type 2 if not type 1. So we see that as a type 1 singularity, so because of this rescaling, supremum of this rescaling sequence of the, so you rescale by lambda I. This is by, when you rescale by lambda I, the curvature rescale by 1 over lambda I. So the curvature norm squared rescale by 1 over lambda I squared. Right. And by the type 1 condition, this is bounded by C over the I squared. So this is less than C, less than infinity, which means that you have uniform curvature bound. So the rescale sequence second fundamental form bound. And the curvature is giving you a C2 bound. If you are uniform, you have uniform bound on the curvature, that means you have uniform bound on the C2 norm. And by Arzela Ascoli, you can, because C2 is compactly embedded into C1 alpha for any alpha between 0 and 1. So you get a converging subsequence in C1 alpha. And because this is an elliptic equation with a uniformly elliptic if you have uniform gradient bound. So once you have a C1 alpha bound, then you have uniform gradient bound, which can improve the regularity up to C infinity by standard elliptic or parabolic theory. So you have, and the convergence is in C infinity. What does that mean? That means that the convergence are at C infinity graphical, locally graphical C infinity multi-sheeted graphs. So it must be like this. Multi-sheeted graphs locally. And in particular, it wouldn't have this curvature. So if it is not graphical, it might be something like this happening. That at the places that it stops being graphical, there are curvature blowing up. So these are converging to also to the limit of multiplicity planes, but the convergence is not in C infinity because the curvature is blowing up, and it is not multi-sheeted graphs. Okay. Any questions? Okay. So for a type 2 singularity, type 2 singularity. So as we mentioned, no matter whether you have type 1 or type 2, when you take this blow up procedure as we did, so we did give this a name last time. So this limit flow that you obtain, we called it a tangent flow, right? So the limit tangent flow is a self-Schenker. The difference is really just that whether you have smooth convergence or just convergence as measures, the type 1 singularity or type 2 singularities. However, in the type 2 case, because you don't have smooth convergence to the limit, so there is actually some information that you are missing when you take this tangent flow, because you're only fixing a point. So the tangent flow are rescaling, but you are fixing at a singular point. So say in this case is space-time 0, 0. So in type 2 singularities, there are more informations that you can obtain by taking a different sequence of rescaling. You allow the center of rescaling to be moving, to be changing in the sequence. Right. So we will use this actually in the study of contracting convex hypersurface. We will get to that later. But let me introduce this rescaling, type 2 rescaling. So this is called blowing up type 2 singularities. So this is also called the Hamilton's blow-up process. All right. So you choose, so because the curvature is actually blowing up than a rate of 1 over square root of t. So you just choose the point of largest curvature, maximum curvature at that time slice, which is achievable because you are considering compact hypersurfaces. Otherwise, there's a point picking process, which is a little bit more involved, but you can always do that. So we will simplify our lives by considering just compact hypersurfaces at the moment. Say xi is in the time 1 over lambda I square, where lambda I is the rescaling factor, such that the second fundamental form actually achieve the maximum second fundamental form at that time slice. Okay. And what do? We rescale we choose the rescale factor to be equal to 1 over this, not 1 over, it is choose the rescaling factor to be exactly equal to a xi. So that after rescaling, this time slice have a uniform second fundamental form bound by 1. Right? If you scale by lambda I, the second fundamental form norm rescaled by 1 over lambda I. So after this rescaling, you have uniform curvature bound. Then the parabolic rescaling. So this is the flow. And again, not again. So in this time, we're not fixing a center point for the rescaling, but we choose to be rescaling at this changing sequence, xi. It's not rescaling around 0. So you choose xi, you move that xi ti to 0. The rescale sequence has a bound by 1. And moreover, so this is recall that this is a type 2 singularity.
Sorry, Shengwen, is the singularity still at time space-time 0, 0?
Yes, that's what I'm trying to say.
So why is it 1 over lambda I squared? Shouldn't it be like a -1?
Yes, you are correct. So this is you're approaching it from backward. This is approaching 0 from backward, and 0, 0 is still the singular, possibly singular space-time point that you are considering. Okay, thanks. So recall that this is a type 2 scaling, type 2 singularity. So after rescaling, this new flow is going to be, so when we do the parabolic rescaling, we call that the time interval also rescale accordingly. So after this rescaling, so the rescale flow is defined in the time interval, time -infinity to a square times ti. So in this case, your ti is equal to -1 over lambda I square. And by the type 2 condition, so defined on the interval. So the rescaled flow for each I is non-empty in this whole interval. So because so it's always going to time -infinity, but because the flow is non-empty between ti and 0, so after rescaling by a square in time, so you get and move the xi ti to 0 here. So you have at the positive time until a square times the norm of ti, it has to be non-empty. So after passing to a limit, so type 2 condition tells you that this is going to infinity, right? Because a squared is blowing up faster than 1 over square root of ti, norm of ti. So this is converging to, so the limit flow is non-empty on the whole timeline. And this is called the eternal flow. So it exists for all negative time up to all positive time to infinity. Okay. Right, so if you recall, if you want to see an example of eternal flow, so we have this example of translating soliton. This also appears in problem 2 of the problem set, a translating soliton. Because it doesn't change shape and just move in a constant speed in a constant direction. So it exists for all negative time up to all positive time. And they arise as possible blow-up limit of mean curvature flow, translating solitons. So that's why they call translating soliton are singularity models for type 2 singularities. So we will get to examples later. Okay. Right, any questions up to now? Right. Okay, so the next thing we are going to do is, so recall that self-shrinkers are measure theoretic tangent flows that you obtain at the singularities. But so these are singularity models when you fix a blow-up point, fix a zoom-in point. So what kind of self-shrinkers might you obtain? So let's see some examples of these. We haven't got to examples yet. Actually, there are tons of examples. Okay. The first one, the trivial one, it's actually the most non-trivial one because it's related to regularity theory, planes, flat planes. They are self-shrinkers. So planes are actually cones, a special example of cones, and its mean curvature is equal to 0. Mean curvature equal to 0, and as a cone, so the position vector projected to the normal position is also 0. And we will actually, so we will get to the regularity theory of the mean curvature flow. So maybe the next lecture or the one next to after next. So the local regularity that we are actually going to prove is that if the blowup is a multiplicity one plane, so we call that as a measure theoretic convergence. It might have multiplicities when you take the blowup limit. So the flow is regular if and only if the tangent flow is multiplicity one plane. Okay. So a second examples are also an examples that we have encountered before. So round spheres or generalized round cylinders. And because they're time negative one slice, so you have to rescale it accordingly in the dimension. So these are round spheres or round cylinders. They are also evolved by self-similar shrinking. And in order to be the time negative one slice, you have to rescale it by square root of 2t. So the third examples are minimal cones. So every minimal cone is a self-shrinker. Again, minimal means mean curvature equal to 0. And cone means that x perp equal to 0. So every minimal cone is a static solution to the mean curvature flow and also a self-shrinker. Okay. Because it splits off a ray in the radial direction. Okay. A fourth example is an example of what's called the Engelmann torus. But it's actually not the torus that people are talking about. It's not topologically Tn, it's topologically Sn minus 1 times S1. And it's a surface of revolution. It's a so you have say this is xn plus 1, x1 to xn. So you have how do I draw revolution tori? So every cross section, this is the cross section is Sn minus 1, and you're revolving in the around the xn plus 1 axis. So you get a torus. So this is a torus, right? And well, you can Engelmann construct this torus self-shrinker by solving some ODE problem. So because of the symmetry, you can reduce the problem to an ODE. And prove the existence of such solutions. So this is have a S1 symmetry here. So actually, this Engineer's torus example is a very useful barrier when you apply the avoidance principle in mean curvature flow. So you can use it to compare with other surfaces and give you some conclusions. Okay. So also, I will mention that even just in dimension 2 in R3, there are self-shrinkers of arbitrarily high genus. So there are a fruitful of examples. So the singularities can be quite complicated. They can be modeled on quite complicated self-shrinkers for mean curvature flow. Okay, so let me use this Engineer torus actually to give you an more non-trivial example of singularities in mean curvature flow called the neck pinch singularity. You can use the Engineer torus as a barrier to prove the existence of such singularity. So if you start with a initial surface such that it's roughly the shape of a dumbbell, so you want to use the avoidance principle. So initially, this joint hypersurface has to stay disjoint for all time, the avoidance principle. So you want to make these two big, thick part large enough so that you fit in two large spheres, and such that it's disjoint. And you want to also make the neck thin enough so that you can use a Engineer torus to go through that thin neck. So the Engineer torus is a self-shrinker. It will shrink to a point because it's a negative time one slice of a self-shrinker. So it will shrink to a point. This Engineer torus will shrink to a point for time 1. So take time unit 1 to shrink to a point. And if you choose the sphere large enough, say it wouldn't shrink to a point until 2 units of time, then initial mean curvature flow starting from this initial surface is going to develop a so-called neck pinch singularity. So this very thin neck pinch off, because the Engineer torus already shrink to a point. So you will have a pinched neck here, but these two large parts are still here because the inside spheres are still there, and it has to be disjoint from these two spheres. And this is an example that you have a singularity, but there's still something left. So you would want to continue the flow in some appropriate weak sense. So after this inappropriate sense of weak flow, these two thick parts are still going to evolve as topological spheres. So they will become disconnected after this neck pinch. So this can be formulated by the weak notion of mean curvature flow we will get to next time. And these two spheres are going to evolve continuously until they become extinct at 2 round points later. And another notion that I want to introduce is the Gaussian density. So we call, again, the calibrated M denotes a mean curvature flow, the space-time track of a flow. And say at a given space-time x naught t naught, and you choose a factor r, the Gaussian density is going to be defined by the integration of t naught minus r squared of scale r. And by Huysken's monotonicity formula, so as r decrease, then this is the time t naught minus r squared is going to be increased to 0. So as r decrease to 0, this is approaching t naught from past. And this is a decreasing property by Huysken monotonicity formula, right? It's decreasing in time t. So by Huysken's monotonicity formula, this is decreasing. So you have a monotonic quantity, and you define the Gaussian density at the space-time x naught t naught to be the limit because of the monotonicity. So the limit must exist. R go to 0. So given the space-time track of the flow, you can give it, this is a so-called Gaussian density at that space-time. And this density is actually related to another functional. So let me define it first. Fx naught s. So the functional, we call it the F functional on the space of, this is also a weighted area. The F functional on the space of hypersurfaces is defined exactly to be the Gaussian integral on that hypersurface. So these definitions are all related to the Huysken monotonicity formula because you have a Gaussian integral there. All right. So as you can see, the Gaussian density is obtained as the limit of this F functional. And why do we care about this functional? So this functional actually is give a characterization of the self-shrinker. So I'm not going to prove this, but this is also like the first variational formula that we computed. So self-shrinkers. So there are actually minimal surfaces in this weighted area functional. Self-Shinkers are critical point for f x naught. So you choose the center point to be 0. And the tangent flow that you obtain is going to be a self-Shinker, and the f functional of that self-Shinker will be exactly equal to Gaussian density at the singular point that you consider. At x naught, t naught. And the F area of any hypersurface of any self-Shinkers is always greater than 1. And it is equal to 1 on a plane. Okay, so let me give you some numerical values of self-Shinkers of the f function of these self-Shinkers. So at the plane, it is equal to 1. And at the cylinder, so these can be computed explicitly. So you put in this Gaussian integral, and you choose the self-Shinker with symmetry that you have, then you can compute it explicitly. So these are all greater than 1. And so as a corollary of the regularity that we will get to, so there is actually a gap. There is this epsilon dimensional constant greater than 0, such that if sigma is a self-Shinker and is non-flat, so it's not a plane. So the plane has F area equal to 1, but any other has to be greater than 1 plus epsilon. This is a dimensional gap. Okay, any questions? Okay, so this will be deduced as a corollary of the local regularity theorem that we deduce in the forthcoming lectures. And so this Gaussian area is greater or equal than 1. So if there are some point here, well, if a point is reached by the flow, the tangent flow has to be non-empty. And if it is non-empty, it has to be at least 1. So theta is m at x naught t naught is greater than 1 if and only if x naught t naught is reached by the flow. And of course, if it is not reached by the flow, you do rescaling, it's an empty set. Its Gaussian density is 0. You get an empty self-Shinker. And by the regularity theorem that we will prove, and it is equal to 1 if and only if it is a regular point. So this is what we will get to. Smooth regular point. Okay, so before we take a break, let me give you a further application of the monotonicity formula and estimation of the extinction time. So see that we have claimed here that if a point is reached by the flow, x naught t naught, so if x naught is in the time t naught, then the Gaussian density is greater or equal than 1. So if the flow is still non-empty at some time t naught, so if non-empty, you can always find such a point that is reached by the flow. But otherwise, the flow doesn't exist at that time slice. So which means that by definition of this Gaussian density, it is equal to, so 1 is less than this Gaussian density. By definition, it is equal to so the integration is on this times induced measure on the hypersurface. And by the monotonicity formula, so T naught is sometime greater than 0. So if you choose by monotonicity formula, and you choose R squared to be T naught, then you have, now you're integrating at time 0 slice. And the exponential part is less than 1. So you have which is equal to the area of the initial surface. Okay. So this gives you an upper bound on the extinction time. So if there is something at time t naught, then t naught, so the flow has to be extinct before t less or equal than. So you take the area of the initial surface and to the power n over 2 and divide it by 4 pi. Right. So finite area surface are going to be extinct in finite time. And you see that even if the flow might, the initial surface might be quite large in the support, like having a very large spine. If the spine is not going to increase the area too much, then the extinction time of this guy is not much larger than just the round sphere. So because the tip is going to contract to the origin in a very fast rate. So the extinction time of these two guys are comparable. Okay, so it is 1 hour. So let's take a 5 minutes break before we continue. And let me know if you have any questions. I also forgot to take the attendance last time, so I'm going to take a picture now.
Can you scroll up to the page before?
Yes.
I think I missed something.
So please interrupt me during the lecture if you have any confusing point want me to clarify. Okay. Otherwise, I might have rushed through too fast.
So are there any continuity properties of either the Gaussian density as we take blowups?
Right. Yeah, I think I forgot to mention this. Right, so the Gaussian density, that's a good question. The Gaussian density, by definition, because it's taking the limit of a decreasing function. So by definition, it is an upper semi-continuous function on the space-time track of the flow. Right, so let me write it down. Theta is an upper semi-continuous function on the space-time track. So it might go up, and it actually will go up at a singular point, because if you just look at the self-shrinking sphere, so you take a sequence of regular point whose Gaussian density is just 1 in the limit. So sequence of space-time point converging to the limit round point that you converge to at the extinction, and that Gaussian density. So we give the value here. So say S2, it's 4 over E, it will jump up. Okay.
Yeah, and they were due in yesterday, so hopefully if we do get any more information, we can feed that back to you.
All right. Are there any other questions that you might want me to clarify? All right, so there are also some other implications of the monotonicity formula that are important in singularity analysis too. So I also put some of them in the exercises. So for example, if you have, you can deduce from the monotonicity formula that there is this constant that only depend on the initial hypersurface, and the flow, the mean curvature flow starting from that hypersurface, initial hypersurface, is going to have Euclidean volume growth at all time and all scale. You have a uniform bound on that. So the area, so these are n-dimensional hypersurfaces. And at any time later, you intersect at a ball radius r, and at any center point, less than this. Sorry, there's a typo here. It should be C, depending on sigma naught. So there's a uniform bound on the volume growth. Oh, sorry, this is n, not 2. So the area of a hypersurface are going to be behaving like the Euclidean n-dimensional hypersurfaces. And there's a uniform bound on all scale. So this is true for any r, any size ball, and any center point in r+1, and also any later time. So it means that the areas, even if it develops singularity, the areas are not going to concentrate too much. So there's a uniform Euclidean volume growth. One second. Okay. All right, so this is going to be left as an exercise. And its proof is by making use of the F area, the Gaussian area that we introduced. Okay, so next, so as we have said, the self-shrinkers are singularity models of the mean curvature flow. So to study singularities, it's important to have classifications of self-shrinkers. So unfortunately, we don't really have much classification results known for self-shrinkers because it's as hard as the classification problem of minimal surfaces. in certain situations, we do know some classification results. For self-shrinkers. So in 1D, this is by Gage and Hamilton. We will also use this to give a quite complete description of shrinking curves in R2. In 1D, there's a classification due to Gage Hamilton saying that the only embedded shrinking curve is S1 or straight lines. So these are the only one-dimensional self-shrinkers. We do have a complete classification in dimension 1, but starting from dimension 2, it's far from any complete classification. So the partial results that I want to mention here. So in dimension 2, this is a result due to Brendel, saying that any self-shrinkers, embedded self-shrinkers again, of genus 0 are either planes, round spheres, or the round shrinking cylinder. This is S1 cross R. This is S2. This is R2. So these are for embedded. Even in dimension 1, there are examples of immersed non-embedded examples. So I put some other examples in the notes too. They are looking like the shape of some flowers. So there are, for example, some self-shrinking immersed shrinkers of such a shape. And another classification result that I want to mention is for mean convex self-shrinkers. In this case, we also do have complete classifications. So this is due to Huisken, who proved it under the condition of uniform bound on second fundamental form and polynomial volume growth. And then it is actually true without any of these assumptions. And this is due to Coding and Minicosi. So these are mean convex shrinkers are only SK. Again, you scale by square root of 2k and minus k. So these generalized cylinders are actually the only possible mean convex self-shrinkers. And recall that we have deduced from the evolution equation that the evolution of mean curvature along the flow satisfies the weak maximum principle. So if it is initially mean convex, I recall that mean convex means that mean curvature greater than 0 or having a sign, then it will stay mean convex for all time. And especially when you zoom in singularities, you can only get singularities modeled on these generalized cylinders. So in the mean convex case, we do have what kind of singularities you might expect, what kind of singularity models you might expect. Okay. So as we will use this later, so let me give you an idea of how they prove this. So I'll give you an idea of the closed case. So when it is complete non-compact, it's usually harder to do analysis because the maximum principle for a non-compact case doesn't just hold without conditions. You have to have some control of the geometry at infinity, but the idea is the same. So proof of closed case. In the closed case, you can directly apply the maximum principle. Right. And I just sketched the idea. So we have deduced the equation for A and H. And by some product rule, you can deduce that at the time -1 slice, which of the self-shrinker, the quantity A squared satisfies this equation. Let me move this a little bit leftward. Minus the position vector. So gradient of that functional inner product with the position vector plus the gradient of, again, this function. So in particular, the right-hand side is greater than 0. In the mean convex case, the H are all positive. And by the maximum principle, so at a maximum point of this quantity A squared over H squared, the gradients terms are always vanishing at the critical point. And the Laplacian having a sign at the maximum point, which has to be negative. And this is going to be a contradiction to the right-hand side being greater than 0, if it is not constant. So by maximum principle, it implies that A squared over H squared has to be constant, which means that all these terms have to be vanishing equal to 0 and gradient of A squared over H squared. And if this is a constant, it implies that it is a space form. In particular, it is constant curvature has to be spheres in the closed case. Okay. Any questions? So let me end this singularity analysis part by some questions that some issues that are still in this subject are not known. So some conjectures, perhaps. So first, right. So a first conjecture is the self-shrinking angular torus. That was conjectured to be the only self-shrinker of genus 1. Unique among closed self-shrinkers of genus 1 in R3. So this is in general not known yet. And also, as we have mentioned before, so when you do this zoom in process and take tangent flow, we only say that a tangent flow because the tangent flow that you obtain in the limit might depend on the choice of the subsequence. And this is also the not necessarily conjecture, but I will mention some results that uniqueness of tangent flows. So in general, you don't really know any uniqueness of the tangent flow that you might obtain at a singular point. But in certain cases, you do know. So this is know by. So Felix Schultz proved that if a tangent flow is a compact, closed one, self-shrinker that you obtain, then the tangent flow that you obtain is independent of the choice of the subsequence. And also by Kolding and Minicozzi. And also by Chodosh and Schultz. So the tangent flow are unique if one of the tangent flow. If one of the tangent flow that you obtain is closed or these generalized cylinders or asymptotically conical. So the generalized cylinders uniqueness are due to Kolding and Minicozzi, and the asymptotically conical ones are due to Chodosh and Schultz. Then it's going to be independent of the subsequence. Then all tangent flow are the same. So even if you are a cylinder, because the axis of the cylinder might rotate, right? You might, at one scale, a subsequence you see a cylinder like in this axis, and in other scale, a priori, you might get another cylinder. And the uniqueness tells you that it wouldn't happen. If it is a multiplicity one cylinder that you obtain as a tangent flow, as one tangent flow, then all tangent flow has to be of the same axis, the same cylinder. And this is not happening. And another issue is that when you do singularity and this tangent flow, blowing up singularities, is the issue of multiplicity. And this is Ullmann's conjecture, probably the most important conjecture right now of in mean curvature flow in 3 dimensions. And nobody has a clue how to deal with that yet. So in R3, That's where he made his original conjecture, that all the tangent flow that you obtain as a measured theoretic limit, so a priori it might have multiplicities. But Ilmanen's conjecture is that they all arise in multiplicity 1. Okay. All right, so any questions?
What do you mean by multiplicity here?
Right. So the tangent flow that you obtain, so you have chosen, say, a sequence of ti going to 0. So this is going to a self-shrinker in measure. So the self-shrinkers that we have a self-shrinker, embedded closed self-shrinker is a self-shrinker, but because this is a measured theoretic convergence, so if you multiply by any integer multiplicity, say n, possibly with multiplicities. And this multiplicity actually has to be integer multiplicity. So this is due to the compactness theorem that we will get to. So it wouldn't have like fractional multiplicity in the end, but it might have integer multiplicity as a limit of some multiple of a self-shrinkers. And the conjecture is that this n has to be 1. This integer has to be 1. Okay.
Thanks.
Okay. Thanks for the question. All right, so the next thing we are going to do is to use this monotonicity formula and this classification of singularity to give a description of the behavior of evolution of convex hypersurfaces. So unlike the examples that we talked about last time, for graphical hypersurfaces, it will stay graphical for all time. It doesn't have a singularity at all, long time existence. But for convex hypersurfaces, it does have singularity. Convex does have singularities, but we do know that there's only one singularity. And the only one singularity is when the surface actually becomes extinct, and there's no other singularity in between. Okay. So first, we notice that convexity automatically implies compactness by Meyer's theorem. So because convex hypersurfaces are having all the sectional curvature to be positive, which implies Ricci curvature to be all positive. And Meyer's theorem tells you that if you have uniformly bounded, if you have a uniformly positive Ricci curvature, then the surface have a diameter bound. In particular, it has to be compact. So convex, as we have mentioned before, it means that the second fundamental form is a strictly positive definite matrix for some delta greater than 0. This means convexity. So the first thing that we want to claim here is that type 2 singularity cannot occur for convex hypersurfaces. So if type 2 singularity cannot occur, then we only have type 1, and we will have uniform curvature bound for the rescaled flow. So we have smooth convergence, as we have explained before. In particular, the blow-up rate of the curvature is at most 1 over square root of t. And this can be seen by the type 2 blow-up process that we have done before. So recall that as a type 2 singularity, you can, in the first half of the lecture, if a type 2 singularity so we did a type 2 blow up by centering at different points. You blow up at the maximum curvature point. And the rescaling factor is equal to the curvature at that point. The sequence of rescaled flow. And this flow is going to be converging to an eternal flow. This flow for each I is defined for t in so we have deduced that this is converging to a limit flow, which is eternal by our previous deduction. Means that it's non-empty for all time, right? Non-empty for all t in. However, in the convex case, you don't have eternal flow. So recall that we have deduced the evolution equation for the mean curvature and for the metric tensor. Sorry, for the curvature tensor and the metric tensor. So recall that the evolution equation of Aij minus delta Gij satisfies the tensor maximum principle. This was in I think the last lecture. Okay. And in particular, if the surface is initially convex, it means that there are some delta greater than 0 such that this tensor is positive definite. And by the tensorial maximum principle, this is preserved for all time and also preserved when you take the limit flow. So in particular, when you obtain this limit flow, this is also satisfied. So this is a scale invariant quantity. It's preserved when you take the limit 2. And then this is a contradiction because any hypersurfaces satisfying this condition has to be compact. By Meyer's theorem. And in particular, it cannot be eternal by the avoidance principle that we talked about multiple times. To compare with enclosed with a large enough sphere, it has to become extinct in finite time. So this is the proof that type 2 singularities cannot occur for convex hypersurfaces. And right now, what do we have? We have, because it's type 1, and we know that the convergence then has to be smooth locally as graphs. 1 over. So still, we might have to pass to subsequence, and the tangent flow might depend on subsequence. So we choose Ti instead of T because not yet the full limit. Smoothly as graphs. And by the classification, so that we have just proved, so convexity obviously implies mean convexity. So you only have self shrinkers as limit, which can only be round cylinders or round spheres. Right? And in fact, in the convex case, because you have uniform convexity, and if it is a cylinder that splits of an R factor, then it will not be uniformly convex. So the only uniformly convex one is the round sphere. Okay. Can only be Sn. The only uniformly convex shrinkers. So we recall that convexity is also preserved. And using the type 1, we can also rule out the multiplicity here. So recall that the limit flow is, well, the tangent flow is a self-shrinking Sn, but you must still have tangent flow converging in multiplicity 2 to, say, locally graphically to a round sphere. But then this is impossible because, well, you can view it in multiple ways. So if it does have multiplicities, so the limit is mean convex. Oh, sorry, the limit is convex. So if you have two sheeted, so these are smoothly as local graphs, they're sheeted. This cannot be convex, for example, because the outside sheet is convex inward and the inside sheet is convex also inward. So there's not a sign. So for this region, the inside sheet is convex outward. So it's not going to be a mean convex. It's not going to be a convex hypersurface anymore. And recall that convex are preserved. So this is a violation. Okay. So only multiplicity 1. And this tells you that uniqueness to limit flow because round spheres are rotational symmetric. And there's only one. So this is actually a full limit. Does not depend on subsequence. So which means that so this is the analysis at the first singular time. And at the first singular time, we actually see that it's asymptotically actually, so if you put the negative t square root factor to the right-hand side, so you see that sigma t is converging to, is converging to converge to a round point as t go to 0. So nothing is going to be remained after the first singular time. Okay. Okay. So that's the description of evolving convex hypersurfaces. Any questions or confusions? All right, recall that, so this is analysis at the first singular time. Right now, we don't really, we don't really have access of the technology, the tools to analyze non-first time singularities. And we don't even know that whether the singular times are discrete or not. So the first singular time, before that is always smooth. But we don't really know that there might be, from future, there might be singular times clustering to this particular singular time. Might not be discrete. But actually for singular times with these cylindrical or spherical singularities, we do have the backward discreteness. So if there's a singular time, you can actually find a small enough time interval that there's no singular time that are priori to it, but there might be future singular time that are converging to it. So these are something more involved that we won't be getting into, but I'm just mentioning this to show you that how complicated singularities or singular times might be, even in dimension 2, this in R3. Okay, so the next thing that we're going to analyze are curve shortening flow. So this is the only other case that without any convexity assumptions, we do know completely how the singular behavior is. So next, curve shortening flow in R2. So this is Grayson theorem. Without any convexity assumptions. It will become convex after some time and shrink to a round point in finite time. And this is also the only singularity being its extinction time singularity. So I would also like to remark that the proofs that I gave here, and also in the previous convex hypersurface case, and also this Grayson theorem, these are not the original proof. This is because so the proof of both of these theorems actually appear before the monotonicity formula approved. Monotonicity formula approved something like 1989, but these are the convex hypersurfaces converging to a round point is proved something like 1984, and the Grayson theorems are even earlier. They don't even know the monotonicity formula or the singularity model, so they will have to do really hard analysis to show that intrinsically the hypersurfaces or the shrinking curves are getting convex and converge to some round point in finite time. So we do have a much simpler proof as we have this knowledge nowadays. Okay. And it's incredible that without the Monotone Institute, how they can deduce using complicated computations. Right. Let me draw a picture. So this is a snake picture that people talking about curve shortening flow always want to draw. So say you have, no matter how complicated or non-convex your initial hypersurface is, so they will rewind themselves under curve shortening flow. Will become less and less rewinded, and shrink to a round point. So let's prove this. So again, we apply Huisken's monotonicity formula in the 1D case. And so we can choose Ti going to 0. So without loss of generality, we can assume the first time singularity is at time 0. We can translate to time 0. And we can translate the singular point to 0 too. Okay. So first time singularity at 0, 0. Right, so you consider the rescaled flow. So gamma I to be defined by gamma Ti, and you rescaled it by 1 over negative square root of negative Ti. And by the monotonicity formula, it tells you that this gamma I, after rescaling, so in 1D case, you only have the geodesic curvature. The mean curvature is equal to the geodesic curvature and is equal to the full curvature. This is converging to 0. All right. So which means that on any compact subset, BR in R2, so this weight function is going to be, so you have a uniform bound. And of course, on compact subset, the position vector is less than not projected, of course, less than R. So you have uniform bound on these quantities and this weight too. So this tells you that, and this is converging to 0, right? So this tells you that K, the geodesic curvature, is uniformly in L2 for this sequence. And the curvature is the second derivative. So which means that the sequence gamma I are uniformly. So you have uniform L2 bound on the second derivative. They are uniformly in the Sobolev space W22. Okay. And actually, these are curves. As subsets of R, they are uniformly in W22. And so in this one-dimensional case, we will be able to apply the Morey-Sobolev inequality. So it tells you that when n is less than pk, then the Sobolev space WKP Rn is compactly embedded into the holder space CRA. So in particular, when your n is equal to 1, k and p equal to 2 in this case, we do have gamma I are uniform in C1 1/2. So you do have a C1 alpha bound. And because these are all satisfying elliptic equation as self-shrinkers. So again, by the standard elliptic theory, so C1 alpha convergence will be able to improve to a C infinity convergence. In C infinity. So once you have C1 alpha, you will get C infinity, and locally as graphically. All right. And in this case, so we call that, so let's go back to the analysis of the singularity of curve shortening flow. And so in the first half of the lecture, we have this classification theorem. So in 1D, the embedded curves, shrinking curves can only be S1 or straight line. The embedded ones. And we see that this limit gamma I can only be integer multiple of S1 straight lines. And we can very easily rule out the multiple of S1. By a similar argument to the previous case, by the connectedness, right? If you converge to, because S1 is compact closed, if you're converging to S1 with multiplicity for large enough, and it's converging smoothly, right? So for large enough I, these two sheets has to be separated. Gamma I is disconnected. This is a contradiction because the gamma I are just rescaling of some time slices. Right. Okay. Too far away. I'll write it again here. Gamma I is just the rescaling of this thing. It is a time slice flow, and we assuming that 0 is the first singular time. So before that is still a perfectly embedded, connected, closed curve. So this is a contradiction. Right. So we still have to rule out. So in the end, we will see that only multiplicity 1 of the circle can occur as a tangent flow at the first singular time. Okay, so to rule out high multiplicity of R as tangent flows. So I will be a sketchy here because let's finish this example. So recall in problem 1 that I asked you to deduce the evolution equation of difference of graphs. So if it is multiplicity over R, the tangent flow, say it is multiplicity over the flat straight line, then for large enough I, the flow can be, so because we also have deduced that the convergence are smooth, C1 1/2 and then C infinity. So they are locally smooth graphs and they are separated graphical solutions locally. Let's use U1 and U2 in this case. All right. Okay, I think I use the index I instead of M. All right, then we can renormalize this sequence of evolving graphs to be the difference (0, -1 time U2, 0, -1). So in particular, Wi equal to 1, normalized to 1. And from problem 1, we have the evolution equation of difference of graphs. So Wi satisfies evolution equation. dtwi is equal to delta KL minus AKL grad U dKLU plus some first order term. So we will, so if you have deduced the evolution equation of the difference of the graphs, you will see that this coefficient and also the coefficient of the first order term, they depend on the gradient, and it goes to 0 as the gradient is converging to 0. And because we already know that the tangent flow is a multiplicity high multiplicity straight line. So in the limit, the gradient is 0, and you have C infinity convergence. So the gradients of U1i's and U2i's are converging to 0 too. So this coefficient is converging to 0. And in the limit, we obtain Wi tend to infinity. So this is W. So in the limit, you will obtain a limit function satisfying the linear heat equation. And this is impossible because, right, so because we already normalized it so that W infinity, because for each I, W0 -1 is equal to 1. So in the infinity, this is also satisfied. But because the sheet has to come together in the limit, so Wi. So this is actually, because you are rescaled by square root of -t, it's still converging to height 0. So originally, it has to have height. Right? Because after you rescale by 1 over -t of 1 over -t, it's still having height converging to 0 because these two sheets are coming together. So before rescaling, you must have this height decay. But however, this is you will obtain an eternal ancient solution of the heat equation. This W is greater or equal than 0, violating the Liouville property. So this W have a sign because these two sheets have a sign. And in the limit, it's going to be a positive solution of linear heat equation. And it has to be constant by Liouville's property. So this is a violation because at time -1, some point is equal to 1 and it's converging to 0 as time converging to 0. Okay, so this is what we will talk about today. And so a bit over time. Let me know if you have any questions. So I will stay here for a few minutes more, I guess, in case you have questions. And otherwise, I will see you next week, the same time.